Okay, great. Everyone, today we're really happy to have Arushi Bodas from University of Chicago and FNAL to come here visiting us, give us talk about speeding up the wave-like dark matter searches using entangled qubits. Arushi got her PhD in 2023 from University of Maryland, working with Raman syndrome on a lot of different topics, and mainly on phase transitions and cosmological colliders. She moved to FirmLab, but she also explored some quantum and sensing technology. So today we're hearing her recent work on this direction.
Yeah. Thank you, Jen, for such a nice introduction. And thank you so much for having me here today. I want to tell you an interesting story about how qubits can show some real advantage in the searches for light wave-like dark matter. This work was done in collaboration with Ronnie Honig and Shoitri Ghosh at Fermilab. So let's get right into it. Okay. So dark matter is one of the important questions for particle physics, and there are a host of direct detection experiments that are trying to understand its nature through its potential couplings to the standard model. Now we know that the dark matter signal would be weak. So all these experiments employ a variety of techniques to reduce noise or enhance signal. So on the front of reducing noise, as you cut down on various standard sources of noise like thermal noise, etc., you would eventually hit a theoretical limit for any classical detector state, which is given by the uncertainty principle. Like you cannot reduce your noise below this limit if you're just using classical states for detection. And on the front of enhanced signal, there is no real limit. Like basically, if you have bigger detector, more volume, your signal just grows linearly with it, but it just becomes logistically difficult. So on both of these fronts, you can ask, can one do better, right? And it is possible to do better on both of these fronts if you use some kind of non-classical or non-coherent states. So for example, to go beyond this standard quantum limit set by the uncertainty principle, what you can do is basically squeezing. You can do this because uncertainty principle is only telling you that the area here between the two quadratures, the uncertainty of the area should be the area should be constant, but it doesn't tell you about the shape. So squeezing is essentially a trick to redistribute uncertainty from the variable that you care about into the variable that you're not measuring, not care about. And this way you can go do better than the standard quantum limit. On the other front, if you wanted to do better than linear scaling, you'll have to use something like entangled states. And the general statement of how this helps is these kinds of states would allow you to add amplitude on various components coherently, such that your signal, which is the square of the amplitude, can grow quadratically with the number of components you're entangling. So it can exhibit superlinear or quadratic scaling. And that's how you can gain enhanced signal faster than you would have expected if you just kept making bigger detector or just increasing number of detectors you have. Now, some of these techniques, like these technologies, are becoming more viable with improvements made in the last couple of years, I suppose. For example, haystack experiment, which looks like axions, light axions, already uses some kind of squeezing technique to improve their experiment. I am not aware, or when I started, I thought that somehow entangled states are not kind of showing up as much in experimental kind of landscape. But it is kind of, they're intriguing because entangled states of qubits, for example, are absolutely crucial for the functioning of quantum computers and actually getting advantage out of them over classical computing. Which means that considering how much kind of resources are being poured into this quantum industry, there's a good chance that creation of entangled qubits becomes kind of viable and robust as the time goes. So it makes sense to think, if you had kind of these robust entangled states of qubits, can they be useful for us? Can they be useful for dark matter detection for us? So this is what I would like to explore in the rest of the talk.
Yeah, so just understand
Yeah.
the setup. You mean people have used the Swiss state to increase sensitivity to go beyond SQS, right?
Yeah.
You are not aware of the actual usage to use entangled state to
Yeah.
sensitivity.
Yeah.
So here when you say entangled state, you actually means multi-sensor system, distributed system.
Yes, I know that you worked on this.
Not referring to my, just understand the context of.
Yes.
Say people have not used the entangled.
Yeah, so there are, of course, like some examples, like your paper where entangling systems, like on cavities, has been discussed. I don't know about experimental implementation of this, but I feel like entanglement is such a unique property of quantum technologies. If you are using quantum technology, you should like think what's the best one can do with it, right? And more like qualitative as well as quantitative advantages from it. So.
But do you need a quantum computer for what you're doing? Or not? You don't, right? You just
No.
need entangled qubit states.
Yes.
Right?
Yes. So you do not.
But do you
Yeah.
need states to be entangled at the level that's useful for a quantum computer?
Not at that level. I think quantum computers functioning would require a lot more machinery,
Good,
like
yeah.
correction and mitigation, all sorts of things. Yeah. Yeah.
The the FCC would be
Sooner.
sooner than quantum computers.
How many people claim FCC will be a quantum provider? So.
It's a quantum collider.
Maybe.
Well, it's quantum part of it, but is that what you meant?
No, there are people saying we should be using quantum data processing for the data. They're trying to reach there. So.
Okay, so first I should tell you which dark matter we are targeting. So of course, as you know, there is a huge range of possibilities for what dark matter could be across the mass range, possible mass range. But because we are thinking about coherent addition of the signal, it kind of makes sense to think about dark matter that would also act coherently over the entire experimental setup that you have, right? So the first kind of target could be a ultralight dark matter below 10 eV. And in this regime, the density of dark matter particles is so high that the de Broglie wavelength overlaps. And it actually makes more sense to think about them as a classical field that has some amplitude that's set by the local dark matter density. And it oscillates because it has mass and some virial velocity. That, albeit it's small, it's there, it's 10 to the minus 3. So you can think about this axion field being here kind of with some amplitude oscillating as we speak at the location of the setup. But this kind of model doesn't hold for forever because dark matter also has some distribution in its velocity, right, through virialization. So it will have a spread in its velocity of the order of virial velocity. And because of that, the kind of correlation between axion field kind of decays in time. And that time scale is called the coherence time of this light dark matter. And it's quite large actually compared to the oscillation frequency of the dark matter. And it's basically 1 over v squared. So you get like 10 to the 6 periods of axion oscillations before the correlation is lost. And another way of kind of incorporating that into your model is just saying that there is this phase in this oscillation that kind of changes and gets randomly picked up every coherence time of dark matter. That's one way of incorporating this effect. And this is important because the signal generally cannot accumulate more coherently than this coherence time. So this will become important. It will be important in the rest of that. So this coherence time, for example, if you have a micro EV dark matter, this is milliseconds. And similarly, as you have coherence time, you have a coherence length beyond which you don't have correlation in dark matter field. And that is actually typically 1 over V dark matter enhanced. So for a micro EV dark matter, it's a kilometer length scale, which means if you're thinking about anything in this range, this is a fairly large coherence length, which means you can safely assume that your setup will be within the coherence length of the dark matter. So these are light dark matter. Okay. So what kind of interaction am I thinking about for this dark matter with the standard model? How am I probing it? So for light dark matter candidates, there are two well-motivated particles, so axion-like particles and dark photons. Both of these can have coupling to the standard model electromagnetism through a Chern-Simons term, FF dual kind of term, or a gauge kinetic mixing. And what these couplings do is that if the dark matter is indeed axion-like particle, dark photon, it will actually create a small oscillating electric field at the location of your experiment because of these couplings. So for axions, you would need an external B field. Dark photons, you don't need anything. But basically, the point is to try to pick up this small electric field that's generated by this axion wave. And this is tiny, so you need to have tricks to enhance it. And the best trick that is currently being employed is the helioscope design, right? So you have a resonant cavity with a high quality factor, so it doesn't lose excitations within it very easily. And on if at a certain resonance condition where the frequency of the cavity mode matches the mass of the dark matter, this electric field actually builds up within cavity and gets enhanced by the quality factor of the cavity, right? And this quality factor can be huge, like 10 to the 4 all the way to 10 to the 11. So this is what enhances this tiny electric field, and then you try to read out the power in the cavity and see if there is any excess power. So that's how these cavity experiments work. And this is actually how ADMX work, for example. And so what is crucial for the functioning of these is the resonance condition that the frequency matches. And so when you're looking for dark matter, you would be scanning, right? You would be changing the frequency of the cavity, look for excess power, change it again, look for it. And you scan over frequency and look for dark matter in some frequency range by doing this multiple times, repeating this. Okay. So now what I want to say is that so the same electric field can be picked up and enhanced by a qubit system as well, right? Just like here using cavity, you can also think of using qubits to pick up this electric field. And to see, let's take one example of a most well-known qubit, which is the transmon qubit, the superconducting transmon qubit. And a transmon qubit is nothing but a LC circuit, right? It's just that this inductor is a Josephson junction. So it has this nonlinear element. I'll say more why it's important. But essentially, it's an LC circuit. So it's a harmonic oscillator. And just like any harmonic oscillator, you can quantize it, where the flux through the inductor and the charge on the capacitor are the two conjugate variables in this case. Right? And so you will, get a harmonic oscillator like spacing Fock space with frequency that's set by the inductance and the capacitor of this circuit. So this is just 1 over square root LC that we probably have seen in school. Okay, so the interesting part of why you need Josephson junction is basically with the Josephson junction, it's a slightly enharmonic oscillator. So what this does, it kind of changes the spacing of the levels a little bit. So it's not all these like higher Fock states, they are not equally spaced because of this non-linearity in the Hamiltonian. And so what you can do is basically if you just use very specific frequency that is between the first two, the energy difference between the first two level, you can specifically address just the 0 and 1 level, and you can almost forget about the rest of the higher levels of the harmonic oscillator and have a finite Hilbert space. And then that's how you build a qubit. Typically, you just have 2 levels that you're working with, and that gives you a qubit.
So,
Okay. Yeah.
What is N? What do you mean by N? This is the qubit.
So this circuit is a transmon qubit. This one circuit.
And the little n, what does that
So the little n is the charge on the capacitor in units of 2e.
Charge on C.
Yeah.
And
The phi is the flux through the inductor.
flux.
Yeah.
So it's a charge flux.
Yeah. And okay, so then how would this tiny electric field couple here? So because we have this capacitor, which naturally has a dipole moment, you will, if you have an electric field, you naturally induce this interaction, right, with the dipole moment of the capacitor with the electric field from dark matter. And of course, it will depend on the charge n here, which is one of the conjugate variables. So if I just write this interaction in terms of a dagger, I will see that I have an interaction which has this form with a plus a dagger, which means this interaction can cause excitations or de-excitations, right? And of course, the thing in the front is some things that depend on the qubit parameters, but this electric field is an oscillating electric field. So the strength of this interaction is oscillating as expected because of the dark matter being oscillating. Yeah. Yeah, so this is basically the interaction between electric field and qubit, and this is what will be used to sense dark matter with the qubit. And I will talk about this a little bit more, but basically, even to enhance this tiny electric field, you also need to satisfy some kind of resonance condition where the frequency of the qubit now matches the mass of the dark matter. That's when the signal is maximized. And so even in this case, just like in the case of cavity, you would have to scan, right? You would have to change frequency by in little amount steps and see if there is dark matter or not. But it is, I want to say that it is actually much simpler to tune transmon qubits. And basically what you do is to make this qubit tunable. You typically replace this Josephson junction with a squid. And by changing the flux through the squid externally, you can change this parameter EL and change the frequency of the qubit by doing so. And what I was told is that basically qubit, you can, without actually having to change any physical property of the circuit, by just changing the flux, you can tune qubits by 1 to 3 gigahertz typically, which is much larger than typically in cavities, you can tune it for about by 10%. So for a 1 gigahertz cavity, you can tune it by 100 millihertz. And before that, you have to change the cavity or something. So this is also a very nice feature which qubits provide that I think cavities, as I understand, kind of, it's annoying in cavities. A megahertz. Yeah, so did I say megahertz? Okay. Okay, so now let us actually see how what is really the signal. So with this interaction. Okay,
Arushi?
so actually one more thing you said. So I was talking about transmon qubits, but there are different architectures that realize qubits in different ways. Like you might have heard of atomic systems or ions, in which people also realize two-level qubit systems. And so some of them also have dipole moments. So you can also think about, instead of this transmon qubit, now have a different qubit system with a dipole moment. So you can couple to this electric field, and you also think about using those for sensing. Wait. Sorry.
Arushi? This is from Zoom. Your slideshow isn't
Give
showing
me a
up
second.
on
I
Zoom.
don't know what happened.
It's just the title
Join
page.
again.
You want battery power? The battery. So. Which the battery?
Did you?
I think I went out of Zoom or something. I have feeling.
Oh, your Zoom is
Maybe.
crashed.
I will just
I don't think
join
you're
again.
recording this either. There's only 2 people on. Well, there were only 2.
But it sounds like
Yeah, actually, I am in there.
yeah, you are still in the Zoom.
Okay. Yeah,
You're
right. But when I do this, it's like going here.
Yeah. So back to meeting.
Oh, okay. Okay.
You should be able to be back to
Actually, cancel that, I guess.
Yeah.
And then
Where's your talk?
like here in the keynote.
Okay,
This
so
going.
it's on Zoom. Yeah, it's here. Okay.
Okay. Okay.
Yeah,
I don't know what's
charger.
happening. So my laptop is charged fully.
Yeah. So it
Does that have something else?
I don't know. Let's
Okay,
see if it
fine.
happens again.
Yeah,
Happens
okay.
again.
Sorry about that. Okay, so in the rest of the talk, we will just kind of abstractly think about a qubit as a two-level system talking to this electric field through the dipole interaction, right? So just a 0 and 1 state for our qubit. And here is that same interaction that I wrote down before with a oscillating strength and this A dagger interaction, which allows you to excite and de-excite a qubit. And actually, this is exactly also how lasers interact with a two-level system. And they basically, this is what people, this kind of interaction, how people manipulate qubits in the first place. So this kind of perturbation leads to what is known as Rabi oscillations in two-level systems. Basically, it's just saying that because this interaction excites and de-excites the state, basically, if you start in just the ground state 0, you slowly build up amplitude on one state, but there is nowhere else to go after that. So your amplitude will start decreasing again, and you will the amplitude kind of oscillate between 0 and 1, 1 to 0. And this matrix is basically encapsulating this kind of Rabi oscillation behavior on amplitudes. So this kind of oscillation will be caused by dark matter in our case. And the rate of this oscillation is actually fastest when the frequency of the qubit matches the mass of the dark matter, or on the resonance condition is satisfied. Under that condition, the gain of amplitude, if you start with 0, the gain of amplitude on 1 is just dictated by the strength of the coupling of dark matter to sound model and the time for which you let it run, right? So then knowing this, a simple experiment that one can design is just start your qubit in the 0 state, just leave it for some time, and after some time ask, did you see an excitation or not, right? And seeing an excitation would be a signal. The probability of seeing an excitation is basically this matrix element squared. So it's sine squared of this eta t. And because the strength, we know that the dark matter is weakly coupled, this is going to be small, so it's just eta squared t squared. Okay, great. Now we want to know how this scales if I had more qubits, right? So to enhance signal, if I had more qubits, how does it scale? If I had now n independent qubits, and I ask what is the probability of seeing just one excitation, that would just be n times the probability of seeing one excitation. So that will just grow linearly. As expected, no surprises there. But we want to do better, right? We wanted to do super linear gain in the signal. So the question is, what do you do? Like, what kind of entanglement do you have to create to get a signal that grows faster than just NQ? Yeah.
That's on qubit have many levels. So
Oh, yes, good.
here you only have 2 levels. So what happens to the other levels? Do you get?
Yeah, let me go back. So I was kind of briefly mentioned it, but in the transform qubit, it has the harmonic oscillator part, which is quadratic phi squared, but it also has this like a small amount of phi cube in its Hamiltonian. So for example, the energy it's not a quadratic function of this flux phi. It's actually this cosine function. So if I expand it out to leading order, it will be a harmonic oscillator, but it has a small enharmonic component, like that nonlinear component that causes the levels to shift. So this enharmonic part will shift the levels a little bit. So for example, this dashed line is a pure harmonic oscillator, but this is the real potential.
But is it important for you just to have 2 levels or not?
In the qubits are made, so the qubits are a finite dimensional system, like in Hilbert space. So that's how they kind of isolate a finite. So for example, because the level spacing is not exactly equal, you can just address the first 2 levels by kind of targeting it to this very specific frequency that corresponds to the energy difference between those levels. Now
so then you don't go to the higher level.
Yeah, you with that you will never go any higher, and you'll just stay within the first 2 levels. Now this is how they build qubits. The question of if I particularly need it, not necessarily actually one can have like large level of systems. Why I'm thinking about qubit is because there will be some technology that will be needed to create entanglement, etc., which people have already thought about from quantum computing perspective. So there are already some, for example, like any qubit architecture would need to have certain kinds of gates or certain kind of operations that they can perform on their qubits. And so that people have figured out. So since we will be using some of that, I want to stick to qubits and not kind of any other. Yeah. Okay, so okay, so the question is, how can you do better than this linear scaling here? And the idea comes from kind of looking at the states which are eigenstates of this matrix. Now, let me explain. Yeah.
It seems like if I wait long enough time, the sensitivity is getting better and better.
Yes, good point. So why not just wait for a long time? Yes. So as I explained, so there is a kind of limiting factor in terms of the coherence time that I mentioned before, right? So the dark matter has a finite coherence. And also we will see that the qubits also have finite coherence. Like if you, for example, create a qubit state in a certain superposition, it will basically start losing amplitude on one state because the zero state is naturally the ground state. So from spontaneous emission, for example, it can collapse to zero state, or it can, even if you start with a pure state, you can get a mixture at the end because it interacts with the environment. So a qubit also has some finite time over which it lives in some sense. And so that also limits for how long you can run the experiment. Okay. So actually there are two groups in Japan that kind of proposed what kind of states do you need to create to accumulate the signal, and I'm just going to describe that setup. So first of all, let's assume that you're on resonance, so the signal gain is maximum. And for now, let's just take that random phase that I described that changes every coherence time to be 0. So with this, one can show that there are these like superposition states of 0 and 1, equal superposition states. These are known as just plus minus states. They are actually eigenstates of that unitary operator. And the eigen values are basically just phases with plus some phase for a plus state and a minus of that for minus state. Yeah. And this phase is basically that eta t, the same amplitude that we were seeing in the previous slide. So now it has gone from that sine eta t into a pure phase. Okay. So once you have this, the kind of trick becomes clear. So because I'm gaining these phases, all I should do is basically create, if I have n qubits, create a superposition of these qubits where all of them are in the plus state, plus all of them are in the minus state, right? So it's a superposition state. And now because, as I explained, dark matter has a large coherence length, so dark matter is going to act in the exact same way on all of these qubits. For every plus state, it's going to impart this e to the plus I eta t phase. And they're all going to multiply and basically add up, right, in the exponent. And for the all negative part of the wave function, you get the exact phase, but exactly opposite phase. But basically, the point is that the phases have added as we wanted linearly. And so when I can expect, like when I go to look at the probability, it will be n squared. Right? So this is the trick. This is the state you need to prepare. And let me just walk you through how it is prepared. So the simplest way to prepare such a state is, let's say you start with all of the qubits in just the ground state. You have n qubits. You just need to do a n number of operations with a single qubit gate and certain kinds of 2-qubit operations. Actually, the exact operations are not very important, so let me just skip that. But what these kinds of the sequence of operation does is basically it one by one entangles these qubits. So it one by one creates plus plus minus minus and plus 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 minus minus. So it's one by one adding qubits to your entanglement. And you can check that this kind of circuit actually ends up giving you this exactly this state, which is all qubits in plus plus all qubits in minus. Yeah. So then after that, as I said, just leave it for some time, let the dark matter interact with it. If the dark matter is on resonance, you would expect this state at the end with the phases added up. Now the question is, how do I read out this phase? This is the phase I'm interested in. Now, typically, if you just had a single qubit, if you want to read out phases on plus minus states, you should just read out in 0, 1 basis. This is like the standard interferometric setup where if you want to read out phases, read it out in the orthogonal basis so that they convert into population differences in the orthogonal states. And so you get some kind of cos sign type of thing. And that change in probability tells you about the phase. But here, if I just naively read out in 0, 1 basis, that's going to be chaos because all of this plus is made of 0 plus 1 and other minuses are 0, 1, 0 plus minus. So in the 0, 1 basis, this is some giant superposition made of various states. So what should you read out? So basically the simplest thing you can do is basically just like you sequentially added qubits to your entangled state, you do the exact opposite. You just reverse all the operations that you did here and one by one remove qubits from your fully entangled state. And what you can show that if you reverse this operation, you will one by one remove n minus 1 qubits and they end up in 0 state. But the first qubit actually retains all of this phase that was gained from n qubits. So you basically just transferring all of that phase onto just one qubit. And now you can read out that one last qubit or the first qubit in the 0, 1 basis, right? And when you're reading it out, you'll see that the probability of seeing that qubit in the excited state, that's your signal now. So I will ask, what is the probability of seeing the first qubit, just the first qubit excited? And that will grow as the square of this phase that we gained, which is n squared. So that's the trick. And one more thing is you might wonder, okay, there was this random phase that I talked about before. I set that to 0, but it would be anything, could be anything. How does it change? So it turns out it just adds this cos squared 5 factor, which on average would be half. So you still, that doesn't change this n squared scaling. Okay, good. So the groups that I mentioned before, they had proposed, they had kind of proposed this, doing this kind of protocol to get n squared. It looked great, but I think there are some questions that are still unanswered to really say that there is this n squared advantage remains, right? So that's what I want to talk about in the next rest of the talk. So the 3 questions that I want to ask is, first of all, are qubits necessary here? Or in other words, is there any equivalent setup from conventional experimental literature that can achieve the same thing? So that's the first question to ask. Then the second is, of course, I didn't talk about noise at all. And people in quantum metrology very well know that when you incorporate noise, you are going to lose the advantage slowly but steadily. So basically, if I incorporate noise, how much advantage does actually remain at the end? And then a simple question, there are helioscope experiments already functioning. How many qubits would it take to compete with those helioscope experiments, right? So let's go through these one by one, starting with the first one. So why am I even saying that are qubits necessary? So first thing is, amplitude addition can also occur in classical waves, right? So you can imagine if you had n waves, if they're adding constructively, that your energy or power would scale as n square. So let's say I had some multi-cavity experiment where I was able to perfectly add electric fields all in phase, all at the same frequency. Then wouldn't I expect the power to scale as n square? And this sounds like you're doing the same thing as qubit, but now using traditional cavity setups. And this kind of thing has been observed. So in, for example, these dielectric stacks, like Mad Max experiment. So in that experiment, it's not multi-cavity, it's kind of multi-layer experiment. So you basically have these stacks of dielectric material. And the idea is that the interaction of this wave-like dark matter generates an electric field at each surface. And you can organize these stacks and the dielectric constant of this material such that at the end, they're all in phase. So on some resonance condition, you can actually see that the power that you receive at the end does scale as a number of layers squared, right? So, okay, so since there is already an example like this, one can just question, do I even need to go through the whole qubit thing when there is already something like this existing with the current experiments? But there is a catch. So in these kinds of experiments, people know and they have observed this kind of trade-off, where if you design this experiment where your peak power, like the on resonance, is enhanced by the number of layers or number of cavities for general term, is enhanced by n squared, they have observed that the response of this combined system actually becomes narrower, exactly as 1 over n. So for example, basically what it means that if you have larger number of cavities, yes, your peak response will go up, but you will not be able to test dark matter within the same range of frequencies, or the bandwidth of the response of this system to dark matter becomes narrower, right? And the exact constraint is that the response as integrated over the entire frequency, that always grows only as the total volume or just linearly with the number of components you have. So this is why if you have n squared more, to conserve the area to only grow linearly, you have to reduce the bandwidth or the frequency over which it's active by 1 over n. So this was kind of elaborated on this paper and has also been observed in these like multi-component experiments that people design for light dark matter. Now, so where is this coming from? So this trade-off is essentially coming from these Thomas Reichert-Kuhn sum rules for any harmonic oscillator. So if you just take just 1D harmonic oscillator, quantize it, and you just ask what you just kind of design this commutator and ask what is this quantity. And you can just compute it in 2 different ways. So one is just simplify the commutators and you get this answer. But you can actually expand this commutator and kind of insert a complete basis of energy eigenstates and get this expression at the end, which kind of has this transition amplitude or transition probability here and the difference of energies. So just from like quantization, it's saying that whatever this quantity is, it's fixed by the parameters of this harmonic oscillator. And if you had n such harmonic oscillators, n particles, you would just sum over the left-hand side with n, and the right-hand side would also get summed over, so you just have n linearly on the right-hand side. So this is, as you can see, is going to constrain any operator that couples to your system through X, right? Sorry, any external source that couples to your system through X operator, right? And this is exactly what the electric field is doing. So if all of these particles are charged and they're exposed to some external electric field Ex, then it turns out that the left-hand side of that TRK sum rule is essentially how much power is absorbed by the system by having this external electric field up to some constant. And because of this constraint, the right-hand side says that the total power that is absorbed by the system only grows linearly with the number of particles that you had in the system. So what this sum rule for this electric field example is doing is saying that the total power absorbed by all the particles in your system can only grow linearly with the number of particles that you had in the first place. Or in other words, even if I design the potential such that some of these amplitudes are really large, I will have to do it at the cost of reducing amplitudes for some other n states, such that the total is always n, right?
So here, the potential is arbitrary or analogous, that's quite different potential.
Yeah, I think the only condition is that the potential here should not depend on, I mean, there shouldn't be any p dependent term except for p squared. So actually the potential, sorry, I shouldn't have said harmonic oscillator. It is,
general potential.
yeah, general, it also works for general potential, yeah. Yeah, just the condition, it shouldn't depend on p. That's the only condition.
So it kind of hard to connect those with your previous statement. The previous statement makes sense, right? So you say, I'll have one sensor that have some response. I have other sensor having the same response, and so I can multiply them together. Of course, the response become narrower and narrower. So my quality factor of the whole system seemingly increased, but my bandwidth will decrease by 1/1.
Yeah, but it's slightly different because I agree. Like if the quality of the system has gone up, then the bandwidth should go down. But here it's not in one-to-one fashion. Like the quality, like the peak has gone up by n squared. So you thought quality has gone up by n squared. The bandwidth has only gone down by 1/n. So it's not 1/n squared decrease in the bandwidth.
Yeah.
So it's not exactly equivalent to just changing quality factors.
Yes, change square, but this is the direct result. If you ask a different question, what's my scan rate over 1 decade?
Oh, yes,
The
yes.
Scan rate is unchanged by this.
Exactly. That's exactly what I'm getting at, actually. So yes, so this kind of sum rule for cavities just constrains the response. So literally exactly same thing can be done for the cavity mode. And you get this kind of constraint that I was talking about, where the response of the cavity, yes, it's integral over the frequency that has to only scale with the number of cavities. So if you had n independent cavities, then your response just grows linearly with n. There is no loss of bandwidth, right? Because this is fine. But if you were thinking of this like weird coherent addition of electric fields, and you say that, okay, actually my response goes up by n squared on resonance, then the cavity width, like the width of the response has to go down by 1/n. Yes. And yes, exactly, as Jen was pointing out, this hurts when you think about scanning strategy, right? Because if you knew where the dark matter is and you were just trying to get as much signal at that mass, then this would be great. But you don't know where the dark matter mass is, so you will be scanning. And because the bandwidth has gone down, now you'll have to do more scans, right? So you're going to lose some of this n squared that you gained at the peak when you're thinking about scan rate. It turns out, as Jen was saying, all of the additional advantage that you could have expected from this coherent addition, blah, 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 is completely lost when you think, when you go and kind of work out what the scan rate is actually. So the scan rate is exactly the same as if you just had n independent cavities, collecting signal from them and just statistically adding it. It's exactly the same. So this is interesting because, first of all, then maybe qubits are qualitatively different. But for that, the one worry might be, what if this is something like this also happening for qubits? Is it? Because then you would again lose all that advantage. But it turns out that, first of all, this really relies on this power absorbed being constrained, right? In qubit protocol, you can show that the average energy of the state just before you expose it to dark matter and after exposing to dark matter, it's exactly the same. Even the variance is the same. So basically, it looks like the dark matter is just, the qubit protocol is just not relying on power absorbed from dark matter, right? So it will not be subject to this constraint that we're seeing for these multi-cavity setups. And indeed, if you explicitly calculate bandwidth for the protocol that I showed, you will see that indeed there is no dependence on the number of qubits in your bandwidth. So this is just the response of that qubit system. So it's this normalized signal. And you see that if I increase number of qubits, the rescaled response just lines up. So the width is exactly the same. Okay. Okay, so the first question's answer is yes, indeed, it looks like qubit do behave qualitatively differently than cavities. So yes, they're indeed necessary. So this entanglement of qubits is qualitatively different and necessary. Okay, so now we can go to the second question. Okay, what about noise? If I incorporate noise, how much of this advantage will I lose? Okay, so for noise, there are,
Sorry,
yes,
just contrast, right? So here you're saying I'm doing phase measurement, so I'm not relying on extracting power,
Yeah,
right?
yeah.
So if I come back to your earlier introduction part of your transmon qubit,
Yeah.
Hamiltonian,
Yeah.
it has two computing quantities. One is
Yeah.
phase of the transmon, the
Yeah.
other is amplitude of the charge,
Yeah.
it's the amplitude.
Right.
So you're saying, can I derive and say, if I design protocol sensitive to the phase of the transmon, I'm okay. If I'm design protocol sensitive to the charge amplitude, I will face the TRK limit.
Oh, interesting. No, I think that phase is
It's a
different.
I know
Yeah.
it's a different quantity, but
Yeah. I think the question is, for example, um,
you know, I
So
can
that's
always
interesting.
change my variable basics, right?
Yeah.
On a harmonic oscillator system.
Yeah.
I call one combination of phase, the other combination
Yeah.
amplitude. So all I care is to make sure the one couples to
Yeah.
dark matter, response to dark matter do not transfer energy.
Exactly, exactly.
Right.
And actually, yes, exactly. And honestly, like the first example, like the most basic setup was like start in the zero state and look for excitations. That is actually absorbing power.
Yeah, that's power up.
But because we made these superposition states, they are actually not changing. Like that, their average energy is not changing because they equally made of 0 and 1. So and they kind of remain equally superposition of 0 and 1. So in those states, the kind of cartoon picture I have is like while you're transitioning 0 to 1, you're also transitioning 1 to 0. So your average energy is not changing. So having those plus minus states was, I think, that the trick that you needed to say that you're not actually absorbing power from dark matter. So, okay, so the second question is noise. So in this setup, there are actually different kinds of noise, and they also behave differently. So we have to kind of keep track of them. So the first is, of course, we saw that in the entire circuit, the only thing that is being read out at the end is this first qubit. That's the only thing we read out. And first, there could be just some error while reading out a qubit, right? So that's the readout error. Because we're only reading out one qubit, that has nothing to do with how many qubits there were in the entire system or the time for which I left it on. So it's just a constant error or the constant error that will give you fake excitations at the end. Okay. Now there will also be errors. So when we prepared and kind of when we did these gate operations, there can be error while just performing gates. So these are gate errors. And the most dominant for these like 2-qubit operations, that's typically the largest source of gate errors. And so of course, like the error can happen while performing any of the gates. And it turns out that these entangled states, they're actually, any error can propagate and give you fake excitation at the end. So the total amount of gate error will actually scale with the number of gate operations, which is actually scaling with the number of qubits that you have. So you have these gate errors that are the total gate error we scale with number of qubits, but it's independent of how long you took to finish the whole protocol. Yeah. So depends on NQ, but does not depend on the time. And then there are these last kinds of errors, which are thermal-like errors. So again, every qubit, for example, can kind of spontaneously emit and de-excite, et cetera, or there could be stray fields that can just kind of rotate the qubit, give it arbitrary phases. So these kinds of errors, of course, every qubit will undergo some of these errors. So they scale with number of qubits that you have, but they also scale with the time for which you leave the qubit. Because the longer you leave it, there's a higher chance of thermal excitation, de-excitation. There's a higher chance that it interacts with the environment. So there are these errors that scale with number of qubits, and they increase with the time for which you run this protocol, right? And what these kinds of errors do, they, as I was saying before, they kind of give a finite lifetime to the state, right? So just like for a single qubit, let's say it's a single qubit holds a superposition for some time, or the single coherence time of qubit is tau q, then the entire entangled state actually lives for only 1/n of that time. So the coherence time of this entangled state is actually 1 over the coherence time of a single qubit. So that's how these time-dependent errors affect kind of affect the lifetime of this entire protocol. Actually, sorry, I didn't explain. So the GSD, the specific state that we made, all plus plus all minus, these kinds of states are known as GSD states. So that's this subscript if anyone was confused. Okay, so again, as we saw, like in the cavity, the actual merit of success is the scan rate. Like, do you get advantage in the scan rate or not? And how much advantage do you get when you're scanning? So that's the important criteria. So here is the scan rate. It's basically saying how much frequency did you cover? And for this qubit protocol, it's just 1 over the time for which you run the protocol. And how much time did it take to cover that much frequency? So frequency over time. So that's the scan rate. And here the number of repetitions of this protocol that you have to do, which is equivalent to the runtime, total runtime of the experiment, that is decided by at what depth you are probing, what depth of dark matter interaction you're probing, how small of this strength is, and like what kind of SNR you are looking for. Okay, so maybe I'll not go through all of it, but say that if I just have n unentangled separate qubits just running in parallel, then I would expect the scan rate to grow linearly with the number of qubits that I have. Now, if I have entangled qubits and I go through track all the n factors, so the scan rate, naively, it looks like it goes as n to the 4th because my signal has gone up by n squared, and the scan rate typically goes as SNR squared. So naively, it looks like there's n to the 4th, but of course, there are factors hidden in the error probability, right? Like there were some errors that were growing with the number of qubits, some not. So I have to be careful. And also the time of the experiment is not always independent on number of qubits. So because there are some errors that depend on number, some doesn't. So we have to kind of keep track of different regimes in which different errors can be dominant. Okay. So let's go through. Oh, yeah. So actually, let's go here. So the signal is n squared. So the SNR typically has maybe this plus the square root of number of repetitions. So when I take the square of that, which goes into this scan rate, because the scan rate depends on the linearly with number of repetitions, you would kind of get squared of this S here. Sorry, should I go through it? Much time do I have?
So on a single resonance, the signal noise level, of course, determines how sensitive you are. Right? So that's the square rate. But they are discussing scan rate, which means I want to sum the sensitivity of neighboring ones as independent probes. So how do I add the information there? I add them in quadratic. Like dollar
right.
So that's why.
Yeah, that's why there's a here.
S over n squared. So I think you understand S over n is n squared, right? So but they are a matter of scanning.
Yeah.
Significance of independent measurement on different bands that become dollar chi-squared.
Yeah. Or maybe one more thing I would say is, so yeah, the signal to noise will only go as n squared, but signal to noise has this square root of n repetition. So it's telling me, so basically to get certain signal to noise, you have to repeat the experiment, and the signal to noise only depends on square root n of that repetition, right? Just like any SNR only depends on square root of t total, right? Total time that you run the experiment for. So if I invert that expression and find out how many repetitions do I need, I would get SNR squared, which goes into the scan rate. So that's why you're getting the n to the 4th. Okay. So let's carefully go through different regimes in which these different types of errors could be dominant and see how the scan rate for this entangled qubit state scales and what kind of advantage do we have in the end. So the first regime is when, let's say you have a setup where your gate errors and your thermal errors are very small. So let's say you have only few qubits. They're all individually, they're very good qubits. So they live for longer than the dark matter coherence time. So your kind of thermal-like errors and your gate errors are small. So the dominant source of your error is just readout error in the beginning. So in that case, because you're only reading out one single qubit, does not scale with NQ. So there is no other dependence of n in anywhere. Even your the time for which you run the experiment will just be set by the coherence time of dark matter and not, which has nothing to do with the number of qubits that you have, right? So for small number of qubits, where let's say you have a good enough setup where the gate errors, individual gate errors or individual thermal errors in a single qubit are small, then in that regime, you actually get all of that n to the fourth advantage. So your scan rate would scale as n to the fourth. So here in this plot, I'm showing number of qubits on the x-axis and just the scan rate of the entangled state on the y-axis. For reference, I have this, if I had n independent qubits, that they would just be scaling linearly. The scan rate for that would just be scaling linearly. So this is that reference point. Okay, so the first regime is where you actually have all n to the fourth growth in scan rate. Now,
I'm with paid on more.
Yeah.
So you increase your SNR, S over N at the given frequency, right? So I achieve that 1 over N squared sooner. That's fine, right? Scan rate is defined how much time it takes me to cover
Yeah.
a certain band.
Yeah.
With a certain target,
Yes,
that's
yes.
the parameter, right?
Yeah.
So if I reduce the amount of time spent on this by 1 over N squared,
Yeah.
then I can move on to the next one sooner, right? So
Yes.
the total time of reduction I get in covering the whole space is still 1 over N squared. Although in your significance calculations, well, it's N to the fourth, but the time for me to cover it is still N squared. Right, let's assume every because you didn't change your sensitivity band, you calculated earlier, right? So let me just say frequency 1, I do that, the whole range I claim I cover that. That's my target. Let me move on to the next frequency, next to it, I will cover it.
Yeah.
So the time is I just reduce it by N squared.
No, because basically what I'm saying is that the signal to noise can right?
Yeah, signal noise is N squared.
N squared square root of n, the square root of t, right? So if I find out how much time do I need to spend, then I'll do square of, like when I invert that, then I'll do square of that, right? Actually, the t here is number of repetitions, n rep parameter. Because actually with qubits, you can't just leave it going. So you have to like repeat. Yeah.
So you're actually assuming my target sensitivity
Yeah.
is so high that I need to really do unrepeated measurement. So that's
Yes.
causing me.
Yes.
So any N square measurement, of course, will give me T to the 4, N to the 4th reduction in time. Right?
Yeah. Yeah. So yeah, exactly.
You're
You're
using
right.
extra time just to root
Yeah.
N to buy.
Yeah. So yeah, you're right. Like my assumption is that this eta or coupling to dark matter is small enough that I cannot possibly measure it in one go. Like you have to repeat it to get to that sensitivity. Yeah. You'll have to repeat it. Yeah. You're right. Yeah. Okay. Okay. So the first regime. Okay. Then comes the second regime where, like, let's say I still I now keep increase the number of qubits that I have. Then at some point, these errors that scale with number of qubits, they will grow and they will become comparable or even overtake the error that you have from just the readout error, right? And then you first typically hit the regime where gate errors are typically smaller than individual thermal errors. So you first hit the regime where now your thermal-like errors are dominant, but they're not. You're still in a regime where the coherence time of the entangled state is larger than dark matter, but your thermal errors are dominating. Now in this regime, yeah, you kind of lose one. So your experimental, like the time of the protocol is still set by the dark matter coherence time, has no NQ dependence, but you have this one NQ coming from the error probability. So you lose one power of NQ, and you have a scan rate that scales as N cubed. Okay. Now, after that, if I still keep increasing number of qubits, what happens is the coherence time of the entangled state now drops below the coherence time of dark matter. So if I want to go above, like increase the number of qubits beyond this point, then I'll have to actually reduce the time for which I run the experiment, because my coherence time just does not survive longer than that. And the conventionally people in metrology think that in this regime, you wouldn't actually expect any advantage from entanglement. But actually, some of that advantage lives on. So now we're in the regime where the thermal errors are actually kind of becoming substantial. So you have to reduce the time for which you run the experiment so that they don't blow up. And what you do is basically as you increase the number of qubits, you reduce the time for which you run them such that this combination, like the total thermal errors, remain fixed at some point where you can tolerate that many errors. And then basically the only other n factor where you lose is the time of your experiment now goes down as you increase n. So you lose two factors of nq from this n to the fourth. So your scan rate scales as n squared, which is still better than just having unentangled qubits by one, right? It's n squared still better. And now if I still want to keep increasing number of qubits, at some point, my total gate errors will actually catch up to this maximum error I can tolerate in my setup. And there is no way to reduce this error because it doesn't depend on time. So I can't just reduce time and like make the gate errors go away. That's just, I'm adding qubits and the gate errors will accumulate. So at this point, basically, after using all the tricks, most of the n to the fourth is gone, and now the scan rate only scales linearly with the number of qubits beyond that point. And that is also assuming that if you increase number of qubits further, you are actually having different kind of entangled setups that you are running in parallel. So that is exactly like kind of unentangled qubit, scaling as unentangled qubit. So yeah, in summary, basically indeed, like eventually noise will take away all of the advantage from this entangled state, but you have all these regimes before which your advantage is completely lost. And to see that, like, what is this point where I'm no longer have any advantage? So the gate errors, people have reached like 1%, even 0.1%. So the maximum number of qubits that you can entangle can be as large as like hundreds, 200s, like somewhere between 100 to 1,000, depending on what the gate errors are. So this can be substantially large. Like you can have large entangled states that are acting as sensors and having really good scan rate. Okay. So this concludes the second part of how to incorporate noise. And the last thing that's left is, okay, how many qubits would it take to compete with a single cavity heloscope experiment? So to compare with cavity heloscopes, first we have to find region of frequency space where both are you have qubits as well as you have cavity experiments. And there's of course, this 1 to 10 gigahertz range, which in dark matter mass is like 5 to 50 microelectron volt range, where there are ADMX and other kind of heloscope experiments. And there are superconducting transmon qubits that I talked about. And so we can ask, let's say they're looking for just dark photon, how do they compare? Now, cavities have one big advantage that they're big, right? Like the cavity experiments are big, they gain from volume, while qubits are tiny, or even their effective volume, which actually also incorporates their capacitance, etc. The effective volume is actually small. So it is not trivial to see how many qubits you might need to compare with the cavities. So we decided to compare with two different cavity setups. One is the traditional kind of ADMX style heloscope, which is cooled down such that its thermal errors are minimized. And the second setup is actually something called photon counting readout, which is basically you have a cavity, you let it build up, but instead of reading out power, you read out how many photons there are in the cavity. And that actually can get below the thermal error kind of SQL, standard quantum limit. It can go beyond that by measuring by doing photon counting instead of reading power. So this is a kind of still cavity-based setups. It is using some quantum tricks, but okay, like we decided to be fair and also compare like the qubit setup to this kind of photon counting setup. Okay, so here is kind of the comparison. So you have dark matter mass and the equivalent frequency here on the x-axis, and you have scan rate on the y-axis. So this is the kind of standard haloscope power readout scheme. This is the photon counting scheme that I mentioned. For qubits, we decided to take some parameters that are still good qubits, but achievable with the current technology. So the qubit coherence time is fixed at 1 millisecond, which people can achieve. The gate errors at 0.5%, again, achievable. And yeah, so the cavities are cooled. So they are also kind of performing at their best. So we have a 25 qubit setup and a 100 qubit setup with these parameters. And we actually surprisingly found that, sorry, at least with the traditional power readout schemes, the qubits can actually compete with them at like 40 to 60 micro EV, which is actually not very far. So of course, intuitively, I would have expected qubits to do better on this side of the mass because cavities actually, with the cavities, their volume or their size is linked with the mass that you're probing, right? Because that's the resonance condition for cavities. So at higher mass, the wavelength, Compton wavelength is smaller. So you are actually, to satisfy the resonance condition, you're thinking of smaller cavities. So cavities lose volume as you go to the right. So their signal drops drastically. While qubits actually, their frequency is determined by the capacitance and the inductance. So it actually has nothing to do with the volume of the qubit. So qubits actually don't lose any volume. So that's one thing. Also, qubits have nice scan rate scaling, as I showed you. So I think because of these things, I expected them to cross over at some point. But what was interesting is that they're crossing at like 50-ish micro EV, which I thought it would be much to the right. So qubits turned out to be performing better than I had expected. Of course, the power counting setup is much better because it's also using quantum tricks. It's not classical. So it would be harder to beat photon counting with qubits. But actually, with the photon counting, they haven't figured out how to do scanning because you have to actually do this change, or they have to tune the cavity slowly. So it's still under progress, and there might be some hidden time cost here because you have to change the frequency very slowly. But in the qubits, the frequency can change very fast. So that I also haven't incorporated. So there could be some hidden time costs here that I haven't taken into account. But at least for the known functioning heloscopes, it seems to compete well. And if I think of better qubits where the coherence times are even longer and the gate errors are shorter, all of the crossovers would shift to the right. And then I can also think of having entangled state of larger number of qubits, like 400 qubits, for example. And yeah, they can compete at even lower masses. So that's I think that's the conclusion from here. Okay, so it's the end of my talk. So in summary, unlike cavity-based experiments, there is no loss of bandwidth for entangled qubit states, which means they get to maintain the advantage in scan rate up to some point. If I compare qubits and kind of these heloscope experiments, qubits have the advantage in terms of tunability and this kind of coherent addition that we talked about. And cavity have, of course, advantage in volume, and it is a known technology. So that's also an advantage. But yeah, so it's because of these kind of things, somehow qubits seem to be able to compete with cavity in interesting mass range. And some things to think about in the future is like, as we saw, like noise is really killing the advantage. Like noise really deciding what is the largest entangled state I can create and how much I can enhance. So it becomes important to reduce noise in any way possible. So error detection, error mitigation, error correction. Can we use any of these tricks to just make sure that we can run this protocol for longer and just gain in sensitivity from there? And of course, like there's an interesting idea of like how can you have hybrid cavity entangled qubit setup that might get the volume advantage for cavity and all these other advantages from qubit. Actually, tunability will probably not work because you will still be limited by cavity tuning, but you'll get some coherent addition advantage for qubits and volume advantage for cavity. So maybe the best case might actually just be a hybrid setup instead of just using qubit separate. And yeah, thank you for listening and happy to take questions.
Any further questions? I'm sorry, can you tell me again where does the speed state appear in the talk?
Oh, no, I'm not using any squeezing. Yeah, I was just, no, I was just kind of as an overview, like what are things you can do. So that's, yeah.
Okay. And then follow up on this.
Yeah.
I think your protocol is actually equivalent to squeezing. You
Yeah.
change the arrow into the phase domain. So
Mhm.
yeah. So from certain point of view,
Yeah.
your protocol is equivalent to squeezing. That allows you to go with Heisenberg scaling and others.
Yeah,
Did you
actually,
discuss with your quantum friends?
actually, I want to. So I have a feeling that squeezing and this kind of entanglement, they're very much related. And yeah,
Depends on how you describe. I
yeah,
think the QRS people actually would describe the
Yeah.
protocol that you are using on the qubits as a squeezing vacuum. They
Oh,
they
okay.
say that.
Oh, I see.
So but that I think there's a translation.
Oh, okay,
It's
okay.
really
Yeah. Actually, yeah, that's a good point. So I haven't actually precisely made connection between like in like definition wise, where am I squeezing, and like if I think about which quadratures are actually am I reducing uncertainty in this kind of case. I agree that I think that they're kind of they should be connected and equivalent. But for the kind of purpose, like wherever I've seen, like they kind of generally thought about as different in many cases. So I don't have a very clean answer right now.
Are there any experiments that use
Ah.
this qubits that can?
Oh, good question. So actually, so at Fermilab, Aaron Schwann's his lab, they have some tunable transform qubits, like they have a chip of 4, and the kind of some of the numbers I was mentioning I took from the qubits, like the parameters of their qubits. Yeah, so they are trying to do a protocol of this, like trying to do a prototype of this protocol for with their 4-qubit chip. Yeah. Just to show if it like what are the problems that pop up.
And then they scale it up to 25.
Yes. So the postdoc I was talking to, like she seemed to not worry. Yeah, I mean, if the once you know how to make the 4-qubit thing work, then she thought she can design like a larger setup with like all qubits on the chip and like connectivity, whatever you need. So I think the first trying to do a 4-qubit, and they're also like the first thing that I mentioned, the protocol itself, that came from the Japanese group, and they're also trying to implement. So they have not done entangled qubit, but they have done a single qubit, like the simplest thing, like just see if there are excitations. They've done such kind of search with single qubit, and they're also trying to do a multi-qubit thing. Sorry, the entangled thing. Yeah.
It's only a third.
So there is Formula. I think the Japanese group, they're also trying to do entangled qubit. Yeah. I think so. Yeah. And crazily, I think at Formula there is also someone who can entangle cavities. So
anytime anything you want. If you work with the chemical experimentalist, you can risk yeah, so they do there's a group of experimentalists doing entanglement study anyway, not for that matter. They are just
right.
do those for general quantum computing or alternative quantum computing operations.
Yeah.
So it's a natural thing to do already for quantum computing people.
Right.
So what we bring to them is you know, before you reach your general quantum computing, maybe you can deform your system for us. Right?
Yeah, because for quantum computing, you would need like error correction, all sorts of extra things. Yeah.
As I said,
Yeah.
way future.
Exactly for those things. Exactly. Yeah.
You're saying that, yeah, you don't need to get to that limit. You
No,
want to start doing measurements.
Yeah.
People are already.
Yeah, they're starting.
Okay, any other questions?
Yeah, I guess I'm also curious about how is the stability of that multi-qubit CMOS quantum solutions nowadays?
Oh, what is the feasibility? So I know that like people have created entangled states, like GSZ entangled states, not in the plus minus basis, but just 0, 0, 0, plus 1, 1, these kinds of GSZ states. Yeah, so the people have created states of up to 30 qubits and with good fidelity, like 90% fidelity. and like maybe up to like 100, but they're not very good. Like they could decohere much faster. So yeah.
The gate she used is all the standard gates in quantum computing. So anyone who's trying to develop qubit quantum computing qubit system with gates on,
Yeah, they would have these.
we can realize this. And the gate error is actually low, right? Gate error
Yeah.
sub-percent level. So I think to
Yeah.
realize such a state is not hard on the current stage. To be able to tune it for physics purposes, that's a different story. The gate error for tunable system might be large.
Yeah. And also, I guess one thing to worry about is like, so in this case, like, so the transmon qubits generally sit around this 5 gigahertz. So you would also need these qubits at higher frequency. Now, on that front, I know that David Schuster's lab, they have made a qubit of 70 gigahertz as a demonstration that you can actually build transmon qubits at higher frequency. So I think with quantum computing, they have no need to make qubits at any other frequency. Just take whatever reliable frequency for the qubit and just do quantum computing with it. But it just tells me that it's possible that you can actually make transmon qubits even at higher frequencies than usually people consider in the industry.
Great. Okay. Let's thank Arushi again for the excellent talk.
Thank you so much.
She will be around until later today, but she wouldn't be here for a speaker dinner. So if anyone wants to join us for lunch, let me know. We can go for lunch, and then you can find her in the FTPR business office to chat more.
Thank you.
Okay, thanks. So I think you stop sharing your screen. Some error happened.